Okay, so I've cleared a little bit of space for a graph to be written right here, and I've got our equation. An absolute value function in the form of this stuff is graphed in the xy coordinate plane where a, b, and c are constants. Graph f of x is equal to negative absolute value of 2x minus 6, all plus 1 in the coordinate plane. So we're used to graphing our base function. And in general, everything else is going to take this function and transform it in some way or translate it or something. So we need to figure out how we can change this thing. So one thing to remember is when you're trying to look at transformations, this when we do this minus some number, some people call it h, some people call it a. There's a lot of different things. That right there, when we subtract something inside of the absolute value, any function that we transform, when we subtract something directly from our input, before we've ever done the main operation of the function, it's going to move it left or right. That h is how much it's moved left or right. So it's going to look very similar to your quadratic or any of those other transformations that you've dealt with. And then this plus k right here, on the outside, so it's directly modifying your output, your y value, that's going to move it up or down. And a number out in front of this right here is basically how much it is stretched or compressed. So it's how much it suddenly, you have your regular one, it might end up being like, it's going to affect the slope of that. It might make it more narrow. A lot of different things going on. Whoops. Oh, man, no. So it's going to get rid of all of that? No, I blocked it out. It's fine. It's fine. What is interesting about this, though, is that notice you don't have an a on the outside of this. You have a -1, but you've got this 2 right here, which doesn't really fit our form. So what I kind of want to do is I want to think of it, I want to factor a 2 out of this. So we have negative absolute value of 2x minus 6 plus 1. I kind of want to get this off of there. I'm only used to dealing with my 2 being outside of my absolute value. And we can use a property or two of our absolute values to kind of look at this. Now, there are other ways to do this, but I just want to show you a way to use it just using transformations. So one thing I want to do is I want to factor a 2 out of both of those right there. So if I do that, I get 2 times x minus 6 over 2 is 3. Now, if you redistribute that, you realize that that means the exact same thing. It's going to give you 2x minus 6. It's going to be the same thing, it's just written different. Now, what's interesting about this is a positive 2. The positive 2 multiplied by this stuff, it's going to have nothing to do with whether or not the stuff on the inside is positive or negative. It's not going to affect whether or not that stuff on the inside is positive or negative. It's not going to change anything about this. So we can pull that 2 outside of our absolute value. So we're really looking at this. It was just a tricksy doodle in disguise thing. But that's because this is a positive 2. It's not going to play any part in whether or not this stuff inside of here is going to be positive or negative. So when we look at this thing, we can pull that 2 out. And we can say, all right, well, now we're looking at a function that was the absolute value function that was moved to the right by 3. That's what that says. And up by 1. And then, but it was also stretched or compressed by -2. So that negative right there is going to flip it over. So instead of a regular absolute value, which looks like this, it's going to suddenly get flipped over and look like that. The 2 part is going to make our curve a little steeper. The -3 part is going to move it to the right. So in general, we can take our original absolute value, which has us, this is, I'm going to do in red our original absolute value function, just to remind you how transformations work. And we're going to go up 1 over 1, up 1 over 1, up 1 over 1. We're just going to keep doing this forever. So it's going to have a slope that looks a little something like that. And I know this is a 1. It's not written. And I know there's half steps, but that's just the way Desmos gave it to me. And on our other side of things, it's going to look like this. Same exact idea. Just has a negative slope on that side. And if you break an absolute value into its piecewise definition, you'll see why that happens, as we've talked about in class. A little something like that. It's not going to be perfect, but that's okay. We kind of move this down a little bit. Yeah, there we go. And same thing over here. And again, probably move it down a little bit just to make it look a little bit nicer. It keeps trying to snap to it. That's the best I've got for right now. Either way, this is your absolute value function. And what I'm going to do is I am going to go ahead and just copy this and turn it blue. Because this is going to be our final function that's after it's all transformed. So let me just kind of put it right here for right now, just so it doesn't mess me up. So this is what I want. I want to take this and I want to translate it. And I'm going to do this by hand just to kind of get you guys used to that, because I honestly prefer working with these things by hand, with any graph by hand. I feel like this right here is the best place to put it. And this right here was absolute value of x, just a straight up absolute value of x. So we need to figure out where to put our vertex, okay? So our absolute value equation started right here originally, okay? And that minus 3 on our x says move it to the right by 1, 2, 3. So that horizontal shift did that. And then we've got to move it up 1, boop, because of that plus 1 that's on the outside. So even without looking at the scaling, we know where to put our vertex. So that is where your vertex would go. Now, one thing I do want to note is we have this negative. So we've got half of our problem done. We've put our vertex where it needs to go. But one thing that we do have, I need to kind of give myself a little bit more room. I need to select this in a better way. Okay. So I'll put that right there. We moved it 1, 2, 3 to the right and up 1. So that's where it's going to go. But that negative 2 out front, is going to flip it over. That negative part is going to flip it over on that same vertex. And it's going to be like that. And the little scaling part, I don't actually need my rays anymore because they're going to change. But I was just trying to figure out where to put my vertex. So honestly, it's just it's on the right side. It's going to go down. It's going to have a slope that goes down 1, 2. Down 1, 2 for every one that goes over to the right. And so it's got to go through that point. And it's just going to keep on going on forever. As long as it's going down 2 over 1, down 2 over 1. This is the only real hard part, because normally you can just drag the graph, but if you're having to draw the rays, you just really need to figure out where your vertex goes. And the vertex was right here. You could have moved just the vertex itself. I was doing it to illustrate a point. So you can move just your vertex itself, and your vertex moved to the right 1, 2, 3, and up 1, because this says move it to the right 3, This says move it up 1. And then now you're just really using slope because it's linear on both sides, and you're going to use the slope. So going left to right from the vertex, in this case, you're going to go down 2 over 1, down 2 over 1 forever. And on the other side, you're just going to go the opposite direction. You're going to go down to left 1 because it looks, I know it feels a little weird to do that, but you've got to remember what the piecewise function of your absolute value looks like. It just negates that original slope. So the original slope is -2, and now it is, it's like it's positive. It's like it's the opposite on the other side of the vertex. So it will look like that. So you really just have to draw your rays. So your blue one, will end up transforming to look a little something like that. Now this one looks hard, but it's actually not so bad. It is a system of inequalities, but we can actually get through a lot of this with process of elimination without actually graphing them because it's multiple choice. Leia would like to earn at least $120 per month. She babysits for $5 per hour, and then she works at an ice cream shop for $8 per hour. Leia cannot work more than 20 hours per month. Let X represent the number of hours Leia babysits, and Y is how much she works at the ice cream shop. Number of hours, all right. So which graph shows the set of points that represents the number of hours that Leia can work in order to earn at least $120 and not work more than 20 hours per month? So what we're looking for is a graph that represents time. All of these represent time, the number of hours. So we need to actually get the two inequalities that gave us these graphs. So let me just think. The only variables I have here, the only unknown quantities are X and Y, so our hours. So we need two inequalities that we can graph to get some more information. So the first one that we have is, the easiest one, is how many hours in total she works. So we know from right here, X is the number of hours she babysits and Y is the number of hours she works. If you want the total number of hours she can work in a given period of time, it's given to us as it can be no more than 20 hours. So really, the time that she spends babysitting plus the time that she spends in the ice cream shop has to be less than or equal to 20. Because those are our constraints. She cannot work more than 20 hours, which means that the amount of time that she works has to be less than or equal to 20. All right, now let's look at the next. We need another inequality. She babysits for $5 per hour and works at an ice cream shop for $8 per hour. And she wants to make more than $120. So even though this has to do with money, we're still relating it to time. So she works $5 per hour at the babysitting gig. So that's 5 times how many hours she works babysitting each month. And then right here, she gets $8 per hour at the ice cream shop. So that amount of money that she's going to get from the ice cream shop is going to be 8 times how many hours she works there. And she wants all of this to be greater than or equal to $120. So we have our two inequalities, and we can tell a lot of things. We can tell from the shading, we can tell from the X and Y intercepts, but we can get rid of a lot of information using both of those. So there's multiple ways to solve this problem. So I'm going to start off by just saying, instead of graphing them, let's compare their X and Y intercepts, because I look at these and I say, man, these graphs, some of them have different X and Y intercepts, if you notice. Like this graph right here has a y-intercept at y equals 20 and 25. This one is also 20 and 25, but this one is 15 and 20. Same thing here. So really what I need to do is, if I can, instead of graphing the whole thing, maybe just finding the x and y intercepts of both of the lines that are the border of these inequalities, maybe that will be easier than graphing the full thing. So let's find, I don't even need to find both of them, but may as well find both of them, because notice right here, this has an x-intercept of 15 and another one at 20. Same thing here. But notice these are 20 and 25. So let's just look at our intercepts and try to graph them. All right, so for this one, we know the y-intercept occurs when x equals 0. So 0 plus y is less. I'm just going to write the equation because I'm just going to write the boundary. So y is equal to 20. So this point should exist when x is 0, y is 20. This point should exist on our graph somewhere. So this is our our y-intercept of the red equation. And may as well just get them all done, because why not? Notice how easy it is to find an x and a y-intercept. If you want your x-intercept, you set y to 0. If you want your y-intercept, you set x equal to 0. That's pretty much it, because that's this fancy way of understanding what our x and our y-axis are. My x-axis is just the line y equals 0. My y-axis is just the line x equals 0. So if I want to find my x-intercept, I set y to 0. So x plus 0 equals 20. So this should be on my line. When x is 20, y is 0. Or when y is 0, x is 20. And for blue, may as well have them all here. I'll do my y-intercept for blue and my x-intercept for that. And when you're actually doing it, you'll be able to just breeze through it. So for my y-intercept, x is 0. 5 times 0 plus 8y I'm just gonna write the equation for the boundary instead of the actual inequality, just to make it less confusing. 5 times 0 is 0, so we get 8y equals 120. Divide both sides by 8. Y is equal to 120 divided by 8. All right, 12 divided by 8, it goes in there one time with a remainder of 4. And then 4 and a 0 give you 40, so it goes into 40 5 times. Or you can throw it into a calculator, because you should have access to that. So y is 15. So when x equals 0, y is 15 for the blue line. And similarly, we'll do 5x plus 8 times 0, because this is our x-intercept. So we get 5x equals 120. Divide both sides by 5. X equals, all right, well, 5 goes into 12 twice with a remainder of 2. And then 5 goes into 20 4 times. So 24. So it looks like that wasn't 25, that was actually 24 that it seems to be hitting. But yeah, it's effectively it right there. We just go ahead and I'm just going to make sure that it's not a different number. Was that 24? And this looks so weird to me because it doesn't seem to... Anyway, it doesn't matter. Let's see. When we analyze these intercepts... And again, the graph doesn't have to be drawn to scale. And if I made an arithmetic mistake, it's not going to actually matter on this one. So notice, if I were to graph these, I would say that y-intercept 0, 20. So when x is 0, y is 20. That exists right here. My x-intercept of that same thing. So that's this line right here. I need it in red because I'm graphing these. So my x-intercept when x equals 20, y equals 0. All right, that line is good. That is this line. Now let's look at my blue ones. Y-intercept, when x equals 0, y equals 15. Wait a second. That's not my boundary line for that. Well, when x-intercept, when y equals 0, x equals 24. Oh, wait, uh-ohs. This is the wrong graph. But that's a way to discount that graph, and you've already pared your solutions down to only two possible ones. And if you look at both of these, they have the same x and y intercepts, so you don't even need that much. Honestly, if you just find a point that doesn't exist on it, then you can already discount that. Now, for these things, we need to figure out which way we shade. Now, if you had started off with the way that you shade, and a lot of this can be done in your head. A lot of this can be done just by looking at it and saying, okay, well, let me just think about my x-intercepts. And it becomes a lot easier that way. But you can also start off by saying, which way do you shade? Notice my positive y is on the left side, and I have a left stand symbol. Without even solving it, I know that I need to shade downward, because my boundary line is going to be y is less than or equal to something, and that means that all of my y values are below that boundary. So you shade downward when your y value, when your positive y value is on the is separated from the rest of it by a less than sign. Because it's saying once you solve for y, get into kind of like a slope intercept form, you shade below because all of your y values are below that line. And if all of your y values are greater than or equal, you shade up. That's it ends up being very simple. It's something students often overthink. So in this case, let's say I have one of my lines. It does. In this case, it's it might be this one. So my y-intercept was 20. So this one is clearly. I'm going to do this one in red. I don't remember which one I did it. So this one is that line, and the other one is the other one. So if I'm going to shade, then that one is all of my y values are shaded down below. And I could keep on going down forever, and it's not as nice as it could look, but it's all those values down below. And that's because my y, once I move that x over there, is less than that. Now, on this one, same thing. You don't even have to solve. It's just the other line. Your positive y values, once you solve, you'll subtract the 5x from both sides. You'll divide everything by 8. But at the end of the day, your y will be on this side separated with a greater than sign, which means all of your y values will be greater than or equal to something. So that means that we need to look at all of the things above that other line. All of the things above that other line. So if we were to shade the whole thing, we're really just looking for the overlap of both of these because they both have to be true at the same time. So this section right here is the section we care about. That's the only section that should be shaded, because the only place that gets shaded is what is true for both of them. But if you look at the original right here, that is not what was shaded, so this one gets to go away. Honestly, the second that we found out that this section would have been shaded, and it's not here, we could have just gone down to this one. There's a lot of quick tips to make these things a lot faster. Which pair? So we know it's this one, by the way. So we're going to use this graph to analyze this stuff. Which pairs, x and y, represent hours that she could work during to meet the given conditions? So really, we're just going to look at all of these points and see if they're in that shaded region. So when x equals 4, y equals 15. When x equals 4, y equals 15. So this is a little bit like right here. When x equals 4, y equals 15. So this point exists there. So that's inside the shaded region. So yes. When x equals 5, y equals 12. When x equals 5, y equals 12. We have 10, 12.5 is up here. I think it's right there. Now we can go ahead and just plug that back in. You can also use the original equations and see if it satisfies them both. So you can either look to see if it's in the shaded region, or you can look to see if it satisfies both of the equations. And so just go through each one of the points and see if they're in that shaded region. Or, alternatively, if it's kind of hard to see like this one is, go through